Hello, space enthusiasts, and welcome back to Astronomy Daily. I'm Avery.
And I'm Anna. We've got a packed show for you today, from lunch delays and spacecraft rescues to the brightest cosmic flash ever seen. And we'll finish by traveling back in time to the birth of Jupiter.
It's a huge lineup. Let's get right into it, starting with the latest from SpaceX.
That's right. It's been a classic hurry up and wait situation for SpaceX, as they've had to postpone the 10th test flight of their massive Starship rocket again.
Indeed. They first tried to launch from their Starbase site in South Texas on Sunday, but a ground systems issue got in the way. Then they tried again on Monday, but this time it was Mother Nature who said not today.
And it was a very specific kind of not today. Anvil-shaped clouds were the culprit. Those pose a serious lightning risk, and you do not want a lightning strike near a fully fueled rocket.
SpaceX CEO Elon Musk, who was on site, confirmed the scrub on social media.
The team is now looking for the next best launch opportunity. A SpaceX spokesperson mentioned that since they didn't fire the water deluge system, reloading propellant should be a relatively quick process. So hopefully we'll see Flight 10 take the skies soon.
And what a sight it'll be. For anyone new to the program, Starship is the biggest and most powerful rocket ever built. SpaceX's grand vision is to use it to help humanity settle the moon and Mars.
It's an incredible piece of engineering. The vehicle consists of two fully reusable stainless steel stages, a massive booster called Super Heavy, and the upper stage, which is also called Starship. The goal is rapid reusability.
But getting there has been a real process of trial and error. Starship has flown 9 times so far, with the first flight back in April of 2023. The last 3 flights this year have all been, well, learning experiences.
That's a polite way of putting it. On Flight 7 and 8, the upper stage exploded less than 10 minutes after launch, and on Flight 9, it lost attitude control during re-entry and broke apart in the atmosphere. We even saw reports of debris spotted over the Bahamas.
It's all part of the rapid iterative development process, I suppose. SpaceX traced the Flight 7 anomaly to a harmonic response that caused propellant leaks and fires. They've since made hardware changes and adjustments to prevent it from happening again.
So the plan for Flight 10, whenever it launches, is ambitious. The Super Heavy boosters will perform some experiments before attempting a controlled splashdown in the Gulf of Mexico. The Starship upper stage will aim to deploy 8 dummy Starlink satellites, relight an engine in space, and then come down in the Indian Ocean about 66 minutes after launch.
It's a huge step, and it's clear they're looking to pick up the pace. Despite the setbacks, SpaceX has requested approval for an incredible 25 Starship launches from Starbase in 2025. They are not slowing down.
Definitely not. We'll be watching closely and we'll bring you updates as soon as Flight 10 gets off the ground. Now, from a mission waiting to start, let's turn to one that just survived a major scare millions of kilometers from home. This is a fantastic story of teamwork from the European Space Agency. Their Jupiter Icy Moons Explorer, or JUICE, is currently on its way to Venus for a gravity assist flyby. But for a little while, the team on the ground had no idea if it was okay.
Talk about a nerve-wracking situation. On July 16th, during a routine check-in, JUICE just fell silent. The deep space antenna in Spain couldn't establish contact. No signal, no telemetry about its health or status, nothing.
The control team at ESOC in Germany immediately began troubleshooting. The biggest fear was that JUICE had entered survival mode, a last resort state triggered by multiple system failures. But they weren't detecting the intermittent signal you'd expect in that scenario.
So with no data coming in, they had to start making some educated guesses. The team suspected an issue with the communication subsystem. They faced a tough choice. Wait 14 days for an automatic spacecraft reset, or send commands blind into space and hope the spacecraft heard them.
Waiting wasn't really an option. As spacecraft operations manager Angela Dietz explained, that would have delayed crucial preparations for the Venus flyby. So they went with the blind commanding option.
And that is not easy. JUICE was 200 million kilometers away, on the other side of the sun. Each command took 11 minutes to get there, and then they had to wait another 11 minutes to see if it worked. After nearly 20 hours of troubleshooting, a command finally got through.
The successful command manually activated the signal amplifier, which boosts the strength of the signal JUICE sends to Earth. Suddenly, they had contact again, and the spacecraft was in perfect health. It turns out the culprit was a very subtle software bug.
A timing bug, of all things. The software function that controls the amplifier uses an internal timer that resets every 16 months. It just so happened that the function was running at the exact moment the timer restarted, which left the amplifier switched off. What are the odds?
Incredibly small. But as we know, in space, you have to plan for everything. The team has already identified ways to prevent this from happening again. It's a textbook example of calm, methodical problem solving under extreme pressure.
Absolutely. A huge congratulations to the ESA mission operations team. With that drama behind them, JUICE is now back on track for its Venus flyby at the end of August. From a close call to a cosmic bullseye, our next story is about a truly record-breaking discovery. This one is genuinely exciting. Astronomers have just detected the brightest fast radio burst ever recorded. It's so powerful, they've nicknamed it RB Float, which stands for Radio Brightest Flash of All Time.
A very fitting name. The burst, officially cataloged as FRB 2025-0316A, was spotted back in March by the CHIME telescope in British Columbia. CHIME has found thousands of these fast radio bursts, or FRBs, but this one is special.
It's not just about the brightness, right? It's about where they found it. Usually, tracing an FRB is like trying to find which tree a firefly is in from a mile away. But this time, they pinpointed its origin to a region just 45 light years across.
Exactly. That incredible precision is thanks to a new upgrade to the CHIME system. They've added 3 smaller outrigger stations across North America, which effectively turns them into a single continent-wide telescope. This allows them to trace these millisecond-long flashes back to their home galaxies with stunning accuracy.
And the home galaxy in this case, NGC 4141, is practically in our backyard, cosmically speaking. It's about 130 million light years away, which is incredibly close for an FRB. Most of them come from billions of light years away.
That proximity, combined with its brightness, gives scientists a unique chance to study the source in detail. The team found the burst originated near the edge of a star-forming region in the galaxy. This hints that the source could be a magnetar, an ultra-magnetized neutron star that's perhaps a bit older than the very youngest stars at the galaxy's core.
And the story gets even better. Because they located it so quickly, they were able to point the James Webb Telescope at the location. Webb's infrared cameras spotted a faint point of light nearby, which they've dubbed NIR-1.
The nature of NIR-1 is still a mystery. It could be a red giant star or maybe a massive star in its midlife. Neither of these are typically associated with FRBs, which has led to a fascinating theory. Perhaps NIR-1 is part of a binary system, with its gravitational partner being the compact objects, like a neutron star, that produce the burst.
It's a fantastic cosmic puzzle. Another idea is that NIR-1 isn't a star at all, but the fading afterglow of the burst itself. Whatever it is, as Ido Berger from the Harvard-Smithsonian Center for Astrophysics said, this could be the first step on a new path to solving the FRB mystery.
It also adds to the debate over whether FRBs are one-time events or repeaters. So far, RB Float seems to be a one-off. Being able to study the environment of a non-repeating FRB this closely is a huge deal, and it shows just how diverse their origins might be.
Absolutely. It's a perfect illustration of how collaboration between different observatories can unlock new discoveries. Now for our final story, we're coming a bit closer to home to look at ancient raindrops from the formation of our own solar system.
That's right, Avery. Researchers have, for the first time, managed to determine the date and origin of tiny, ancient, molten droplets that came from the neighborhood of a young Jupiter. These droplets were found inside meteorites here on Earth.
Molten rock raindrops from Jupiter? That sounds incredible. How does that even happen?
Well, about 4.5 billion years ago, as Jupiter was forming, its immense gravitational pull started flinging nearby small, rocky, and icy bodies, called planetesimals, into each other at incredibly high speeds.
So these were seriously high-energy collisions. What happened to the rock?
The impacts were so forceful that the rock and dust on these planetesimals melted instantly, creating tiny, molten rock droplets known as chondrules. These spheres, only about a millimeter wide, eventually got incorporated into asteroids, some of which later fell to Earth as meteorites.
So scientists have had these chondrules for a while, but they weren't sure exactly how they formed. What's the new theory?
A team from Nagoya University in Japan and the INAF Turin Astrophysical Observatory in Italy developed a new model. They realized that when these water-rich planetesimals collided, the water would have instantly vaporized into steam. This expanding steam acted like a series of tiny explosions, breaking apart the molten rock into the exact kind of droplets we see in meteorites.
That makes so much sense. So they tested this with a computer simulation.
They did. They programmed a simulation of Jupiter's formation, tracking how its gravity would cause these collisions. Co-lead author, Dr. Diego Turini, said the model spontaneously generated realistic-looking chondrules, and importantly, it showed that the peak of this chondrule production happened right as Jupiter was accumulating gas to become the giant it is today.
And the evidence from actual meteorites backs this up.
Perfectly. The meteorite data shows that peak chondrule production occurred about 1.8 million years after the solar system began, which is exactly when they believe Jupiter was going through its main growth spurt.
Wow. So these tiny droplets are like fossilized evidence of Jupiter's birth. That's amazing. Does this solve all the mysteries?
Not quite. The model doesn't fully explain why we find chondrules of different ages in meteorites. The researchers suggest that the formation of other gas giants like Saturn could have triggered similar events later on, creating more chondrules.
It's a fantastic piece of detective work. It gives us a clearer picture of how our solar system formed and provides insights that could apply to other systems as well. A huge story contained in a tiny ancient raindrop. And that's all the time we have for this episode of Astronomy Daily. From cosmic flashes to planetary raindrops, it's been another incredible week in space.
It certainly has. Thank you so much for joining us. If you enjoyed the show, please subscribe wherever you get your podcasts, and you can follow us on social media for daily updates.
Until next time, keep looking up.
Goodbye, everyone.
Astronomy.